Our third speaker today is Dr. Raymond CHEUNG. Raymond has more than 30 years of experience in civil and geotechnical engineering. He has been involved in a number of mega civil engineering projects. Under the airport course program, including the airport railway, Chatlapkot International Airport, reclamation and West Harbour crossing, before he joined the Hong Kong government in the late 1990s. He is a member of the School Scientific Committee of Landslide Risk Assessment and Mitigation, International Network of Landslide Early Warning Systems, and the editorial board of the Chinese Journal of Geotechnical Engineering. He is currently head of the Geotechnical Engineering Office of the Civil Engineering and Development Department, overseeing the control of geotechnical works, setting geotechnical standards, mining operation and quarrying, tunneling and underground space development, the landslide prevention mitigation program, and the landslide emergency services. Raymond will discuss GEO's recent strategy to step up Hong Kong's resilience against increasing landslide risk due to extreme rainfall events. Welcome, Raymond.
Thank you for the kind introduction, Mr. Lee. Distinguished guests, distinguished speaker, colleagues and friends, good afternoon. Thank you for inviting me to share with you a subject on the landslide resilience. I'm going to talk about landslide resilience strategy, basically evolution from hard to smart over the years. So probably I think all of you know that recently the IPCC has issued the 6th assessment report, and no doubt warning of climate system is unequivocal, and Hong Kong is not immersed to climate change. As you know, one of the natural hazards in Hong Kong is landslide. So in fact, surrounding us, different regions are subject to landslide hazard. And here you can see around Hong Kong, many regions, they are subject to severe rainstorm and landslides in recent years. So very recent case, 2 weeks ago, a tropical storm called Maggie hits Philippines. And it has, up to now, the death toll from landslide and flood already more than 160 people. So the extreme rainstorm or extreme weather, I think it is not a question. The question should be, when the next storm hits, have we prepared for it? So let me first look into what is resilience. I think the first reference to resilience was by the English philosopher Francis Bacon in the 17th century to describe the physical characteristics of an echo and how it bounced back off the wall. And as an engineer, I think we know Rankine, and in his manual of applied mechanics in the 19th century, he described the quantity of mechanical work to produce strain, as spring, or resilience. So many people have redefined the terminology from old days, but one aspect has not changed. That is, there must be something to bounce back from. So I define landslide resilience as an ability to anticipate, prepare for, and respond to hazardous events related to landslides. So in Hong Kong, in the past, we are doing hard work to build our sub-safety system. So we have to know the size of problem. That's why we have a compilation of a sub-catalog. And we need a geotechnical control. We set standards through legislation and internal circular to control the design and construction. We need to maintain stock. That's why we have an assignment of a responsibility and landslide warning. We need a network of rain gauges. We need a forecast too. And finally, it's very important, is a public awareness. So we need a public education. So over the years, we are doing hard work to gradually develop or to build up our sub-safety system from land use planning, standard control, to the other end is a public education. And over the year, we need to measure the performance of the system. For example, here, show you the graph of a landslide risk against the year. So you can see the red bar showing the fatality due to landslide. Upon the establishment of the sub-safety system, the fatality event gradually decreased, and the landslide risk also, we use a quantitative risk assessment to assess whether there's a decrease in the risk. Up to now, we can say that the overall landslide risk in Hong Kong, when compared with 1977, is down to a level less than 25%. And in reality, the last landslide incident that involved fatality occurred in 40 years ago, up down to the 2008. And when we recall the landslide incident report to us over the years, so you can see, on average, we receive about 200 and 300 reported landslide incident per year. So I think our system is capable to manage the landslide incident in Hong Kong. And you can see from this chart, in a particular year, 2008, we received more than 800 landslide incidents. So it is a very severe rainstorm, but on average, I think our system can handle the issue. But is it the end of the story? Of course not. And as mentioned before, in 2008, although we have received around 800 incidents, but in fact, when we look into the aerial photo, we find we have many unreported landslides. They occur on lateral terrain because they were not affecting people at that time, so they are not reported. So we have no complacency. The risk is there. The next question is, can we upgrade our sub-safety system to handle the coming landslide in terms of number, in terms of severity? Can we make use of smarter tool to re-establish the system? So back to the sub-safety system component, because the scope is too large, I'm going to share with you a particular component, that is a landslide warning and emergency service. I'm going to share with you how we make use of smart tool to upgrade this component. So of course, the landslide warning system is run by our office, Geotechnical Engineering Office, as well as the Hong Kong Observatory. And in fact, many people don't know that it is the first territory-wide landslide warning system in the world. It was first established in 1977. The objective is, of course, to alert the general public, to reduce the landslide, to let them know the danger of landslide, and second, to trigger emergency system. This is the first generation of landslide warning. Basically, it's based on the research by Professor Peter Lam in Hong Kong University, as well as the GEO internal study. So at that time, we defined the rainfall threshold curve using the actual day rainfall and the previous 15 days rainfall. And at that time, we have two levels of warning, that is amber and red warning, and we base on 20 automatic rain gauges, and the area basically focus on the squatter dwelling, because this is a vulnerable area subject to landslide at that time. So this graph, you can see different region. The red, yellow, that's the amber, with a 1-day rainfall, 15-day rainfall. We base on this to issue landslide warning. Over the past 20 years, we upgrade our warning from time to time, basically. In previously 1-day and 15-day rainfall, up to now, I think this is the 4th generation. We make use of the so-called 24-hour rolling rainfall, and we use make use of the catalog slope, 4 types of slope, and we make use of the network of rain gauge in Hong Kong. I think up to now we have 120 rain gauge in Hong Kong. We developed this kind of landscape warning system. But can we make use of smart too? Let me introduce you the structure of the warning system. So in this figure, you can see on the left-hand side, we need the real-time rainfall data. We need the forecast rainfall by Hong Kong Observatory. And in the middle, we need the statistical correlation between the landslide frequency and rainfall. And on the right side, of course, we need the information of slope, including the distribution of slope, the characteristic of slope. So the first component is about rainfall. Cloud platform. Nowadays, we upgrade our system. We put all the information, I mean the rainfall information, to a cloud platform in order to improve the system resilience and of course improve the data availability. And we have a more redundancy in terms of telecommunication networks. So you can imagine how much information we have. We have 90 rain gauge managed by GEO, and we have 24 hours a day, and every 1 minute we got a data. So it's a huge amount of data per day. So we have to handle this kind of thing. So that's why resilience, in terms of system resilience, is important to us. Second is about the rainfall, rainstorm forecast. Of course, Hong Kong Observatory, they improved their radar. They use 2 Doppler weather radars to monitor rain cell along South China Sea. The monitoring range improved to 250 kilometers, and they got a nowcasting system to provide us with 1 hour, 2 hour, 3 hour rainfall forecast at every 6-minute interval. So this is not the end of the story. In the middle one, of course, an important one, the core of the warning system is the computation. That is the rainfall landslide analysis. As I mentioned before, we rely on the conventional statistical analysis before, but can we make use of machine learning? Can we make use of a machine learning cloud computation, real-time computation? Yes, we can. When we look at the data availability, we have a big data set in our office. We have more than 60,000 registered man-made slope. Each man-made slope, we have different information, including geometry, performance, drainage, etc. And we got a landslide inventory. And for reported landslide, we have more than 12,000 landslide record. And on natural terrain, we have more than 100,000 landslide record. GI information, it provides us geological information of the ground. We have more than 300,000 GI stations in the territory. Of course, remote sensing, we got the LiDAR information. We have updated LiDAR information, 220 of the whole territory, so we can capture the terrain accurately. Of course, as I mentioned, we have many rainfall information. So can we handle it through AI? And I think AI or machine learning, we have to solve the practical problem using past data. And we develop a mechanistic formula using algorithm to automatically to do the prediction and with minimal or without human intervention. Of course, AI or machine learning, it is a technology. Bear in mind, it's a technology, it's not a science, because we are interested to resolve a practical problem and not to understand how the world works. But in fact, there are 2 major tasks in AI. The first is classification. Some people refer it as a discrimination or supervised learning. The objective is to say what kind of situation we are facing. And the second major task, of course, is prediction, to tell us what is going to happen in future. So this schematic diagram show you the process for our landscape modeling. And first, we have raw data, as I mentioned before. We have a big data pool, and we have to select what kind of feature is important to landslide hazards. So we should establish a structured data set, and then we go into the learning algorithm. Nowadays, we got different algorithm. We have to have some assessment criteria in order to select suitable algorithm. After that, we have to train the algorithm. And after training, of course, we have to evaluate the performance and the algorithm. And I think it is an iteration process until at the end we do the prediction. So back to the first critical activity, that is feature engineering or feature selection. In fact, it is a process of reducing the dimensionality of the input variable in order to capture the key information. That is, we have many parameters. We rely on a professional judgment, experience in order to select most relevant to the subject. So in terms of landslide, of course, rainfall is an important feature, but whether it's a 5 minute, 1 hour, 4 hour, or 24 hour, I think we need to answer this question based on our domain knowledge. And we do the correlation then, and after doing the correlation, we have to verify whether the finding is consistent with our domain knowledge. So whether there's a causal link, is it sound in terms of physics or geotechnical knowledge. So this diagram shows you some preliminary assessment. The y-axis is the correlation with landslide occurrence. The horizontal axis is consistent with our professional knowledge, that is domain knowledge. Now we have a different kind of parameter, the terrain attribute in terms of say for example, the plant curvature, slope angle, catchment area, etc. Geology, the rigorous, what kind of rigorous? Of course, rainfall, duration, intensity of rainfall. When we put it into the algorithm, selection, then we can see from this diagram, for example, rainfall here. So we can, from statistical point of view, this is highly correlated with landslide, and it also match with our domain knowledge. That's why it is a very confident parameter for our follow-up action. On the other hand, superficial geology, in terms of the domain knowledge, it's not very irrelevant. And in terms of the correlation from the statistical point of view, the correlation is also very low. So we will read out from the analysis. The second step is the selection of a machine learning algorithm. And in the world, there's a wide range of the machine learning algorithm, but basically they're based on three kind of algorithm. That is the classification trees, regressions, and neural network. Sometimes people may refer neural networks as deep learning, but there's no consensus in the AI world, an optimum or single best algorithm. So mostly we may select some algorithm to do our analysis. So with this, we can introduce the criteria. And this diagram shows you the confusion matrix. Is quite confused here. And I think it is very simple. We have the actual performance, we have a prediction. For example, on the top left-hand corner, true positive. It means in reality, there is landslide, but in the prediction, it also predicts there's a landslide. So very good. So based on this confusion matrix, we can define different criteria. Say, for example, accuracy, precision, sensitivity, or very common, so-called the ROC, receiver operating characteristic, or some kind of F1 score and other score. And as I mentioned before, there's no single optimum or single best algorithm. We have to test a bundle of algorithm to suit our purpose. So after that, we have carried out some pilot study. We are using a Landslide Island. We use the information ranging from 1985 to 2008, 24 years information. We divided the area into a number of grid. For each grid, the area is 5 meter times 5 meter. So you can imagine how tiny is the area. And we select 3 classification algorithm. So we use XGBoost, decision tree, and random forest. They're very common algorithm in the AI world. And as I mentioned, we have a different feature, and they are multidimensional and nonlinear. Landside inventory, terrain attribute, and geology, rainfall. But our interest is landside prediction. So based on the algorithm, we have carried out this kind of nonlinear multidimensional linkage or analysis. And I'm going to show you some result. So from this figure, you can see we find 95% of the landslide occur in this year duration. They fall within 15% area. It means we can identify the high risk area, the hazard area. I think it's very important in terms of no matter it's urban planning, urban planning or landslide warning is important. And also, we are going to do some prediction. We try loading. I mean, we add a rainfall. For example, here we add 6% of the annual rainfall in terms of 24 hours to the area. So you can see the area of different probability. So far it's a very good, it's almost a blue area. The probability is very low. But when we increase the rainfall loading, you can see the changes. So to 30%, you can easily see the area color with a red, and this area is a highly landslide risk, relatively high landslide potential or probability. I think this kind of tool help us to upgrade, no matter it's a planning or landslide warning system. So it's quite promising up to now. But of course, we need to do more in the future. And second part, after warning, we need emergency services. Of course, we need to see the overall picture after the passage of rainstorm. So we, apart from a UAV, we make use of a satellite technology. Now we have a satellite image every day. So from a desktop or from mobile phone, we can see, we can capture the Hong Kong territory to see the performance of the hillside, to see how many landslides have recently occurred by severe rainstorm. Of course, cloud may be an issue because after the rainstorm, usually the areas, the Hong Kong territory is covered by a thick of cloud, but at least after a few days, we can clearly see the territory. So it helps us to prepare the emergency service and to plan the following up action. So this diagram shows you the area and sharp peak in May 2014. So you can clearly see the landslide trail after the rainstorm. So of course, this is tailor-made for us. We can order a satellite to move to a particular position, to position a particular area, to get a high resolution photograph for our purpose. The second part is also very important in terms of emergency service. We need emergency team, we need rescue team, we need to share information among works department in Hong Kong government. So we developed recently a platform, digital platform called Common Operational Picture. In this platform, we can share real-time information of different kind of hazardous incident. For example, of course, our office is responsible for landslide. We need landslide information. Drainage Service Department, they're concerned about flooding, and tree management office, tree fall, and structural, maybe buildings department, and weather forecast, weather information, Hong Kong Observatory. So we share real-time information on this platform. And you can see on the platform like that, we can instantly see the number of incidents, the geographical location of the incident, the detailed incident in Hong Kong on a desktop or mobile apps. So for landslide, so this picture shows you the distribution of the landslide or particular rainstorm. So we can plan our resources, plan our rescue team, and prioritize our action based on this information. Apart from overall picture, sometimes we need site-specific information. So recently, we think about whether we can make use of robotic technology to help us. In this diagram, you can see, or sometimes they call robot dogs. In fact, it is a mobile platform, and the machine or the robot can climb up hilly terrain. So it provides a mobile platform. But we need some instrument. That is, we have a long-range control, 5G control. We need a vision, we need computation, and we need, of course, sensor to collect data. So we provide the mobile platform with, of course, advanced 360-degree cameras. We have a GPU to accelerate the AI computation. We use edge computation. We use a lightweight LiDAR to capture all the information on the landside site. This shows you the information we collect among the incident. So you can see we can capture accurately the information of a landside site when we wish to do so. So apart from that, we also need, in terms of emergency service, another development is so-called the digital twin, as well as of course, importance of public involvement. And nowadays, we install many landslide debris resistant barrier on the foot of a natural hillside. And basically, we would like to upgrade the barrier to a smart system. And now, whenever there's a landslide occur, if it is a very extreme landslide and exceed the desired capacity of the barrier, then people may call the police, or they may call us and report the landslide to us, and we will send our people to inspect and carry out emergency action. And if it is not exceed the desired capacity and the debris retained behind the barrier, normally the debris will clean up by maintenance department, maybe during the annual inspection, etc. But can we upgrade the barrier to smart system to detect the landslide itself, so they can promise whenever there's a landslide occur? Yes, we can. So, well, the idea is very simple. This shows you the system architecture of a so-called smart barrier system. We need IoT technology. We install some kind of sensor on the barrier. For example, we have an impact switch, we have a depth gauge, camera, and transmission. There's no problem nowadays. So we have a LoRa, wire connection or 4G in the cloud platform, and then through the cloud network, we can access the information on a desktop computer or mobile apps. No matter what kind of weather, whenever there's a landslide, hitting occur in the vicinity, hitting the barrier, so we know the information, so we can plan our action. So here show you the photos, the physical element of the barrier, so you can see the camera, depth gauge, base station, wireless impact switch, etc. So we need a site trial. So you can see from this diagram, we have some kind of test site. We have a field test site being tested in terms of accuracy, reliability, and robustness. So for a particular site, we also develop an emergency plan because we need an involvement of the public. So the site is very close to Queen Mary Hospital. At the back of the Queen Mary Hospital, we have a set of barrier. So it is, of course, it's a smart barrier. So based on this, we have carried out some kind of a debit mobility analysis. We know what kind of situation we have for different volume of debris. So we develop different zone. You can see the color vary from amber, yellow to red. So based on this, we develop an emergency handbook. We have an action flow chart. Basically ask the maintenance people in the Queen Mary Hospital to do some kind of a simple action. For example, to fence off the area, the hazard area, to remove the people in the building, etc. So whenever we receive the signal, we will screen out the signal. If we know there may be a potential risk, we will let them know to do the front action, so they can do the action automatically. So very simple. So finally, this is a conclusion. I think there's no doubt warming of the climate is unequivocal, and we anticipate more frequent and more extreme rainstorms coming, and we need to further enhance our landslide resilience. And we try to make use of innovation and technology to transform our safety system to a smart system. Of course, as I mentioned before, it can't only rely on government action. We have to keep the awareness of the general public and get them involved. But can we go further? I think we can. So we are thinking about digital twin. Can we move further step, transform the subsafety system into a digital twin system? So we are thinking about this approach. I'm going to share with you a 1 minute video showing our G-Info. That is the geotechnical information infrastructure called G-Info. Now, when we assess the system, you can see a two-dimensional information of the slope. Of course, when you are interested in a particular slope, you can see the information, including the photograph, dimension, performance, history, etc. Now, we try to move from 2D to 3D. So you can assess the same slope in a three-dimensional environment, do the measurement, assess the information. Furthermore, we would like to have a 4D, in fact, information. That is, for example, here, it is a Poshan drainage tunnel. So this, because you know there's a Poshan severe landslide before, we install a tunnel as well as a number of piezometer. When we click into the piezometer, it will give you a real-time measurement. You can see through mobile phone desktop, access the information in real time. Every 15 minutes, we have one information. So you can imagine it's some kind of IoT system, digital twin, and we can make use of this technology to enhance the resilience of the system. With this, I think this is all we have. Thank you very much.
Thank you, Raymond. I think it's really eye-opening to see how we have progressed over the years in trying to make our slopes safe. Since time is running out, just a short question for you, Raymond.
Yes.
Do you think we need a lot of resources to add on to your existing system in order to keep our slopes safe to deal with the extreme weather?
Well, in terms of the resources, when we compare, I think we're going to compare with engine works. I think just a tiny amount, I think less than 10% of the resources we are now input into engine works. So I think it is worthwhile to do the investment because, as I mentioned, climate change, we can't avoid this kind of thing, severe rainstorm, climate change. This very deserve to have this kind of investment but in particular, as a government, I think it's deserve worthwhile to do this investment.
Thank you, Raymond. Thank you for the informative talk.
Thank you.